So for chapter 2, we are going to be studying a test case problem of multi-armed bandits. And this is a particular context of problem where we can explore techniques that evaluate the quality of different actions, but we remove from the problem the complexity of the state of a problem, which we usually have to deal with. So normally, depending on the situation of the environment, different actions will have different consequences. But for just this chapter in particular, we have this so-called non-associative setting where we can evaluate actions, but there is no shifting context of how the actions are interpreted. So the purpose of this chapter is to introduce the concept of different action value methods and ways of estimating action values without a lot of the complexity that we'll deal with later on in the book. So does that make sense so far, everyone? Because next I'll introduce the actual problem setting more specifically. So for the remainder of this chapter, we're going to be talking about this so-called K-armed bandit problem. And for these problems, the setup is we just have a choice among K different actions. And the actions don't really mean anything other than after we take an action, we will receive some sort of reward. And that reward is going to be predetermined by how the bandit is constructed. So for these problems, we're going to introduce a particular type of bandit, which is going to make sense in the context of later reinforcement learning problems. But in general, one of these bandits can be any sort of problem where we have, K different options. And whenever we select an option, a reward is drawn from some distribution of possible rewards. And really, the distribution could be anything. We will sort of have the requirement that it has a well-defined mean value. So I've written it out a little more formally here, but if we have, this PR will describe some function over rewards once we select an action here, and from 1 to K. And we're going to, go with the assumption that there is some expected value for a reward given an action, which is well defined. I mean, there are probability distributions that don't have well-defined expected values, because like when you try to calculate it, you get an infinite value. And that would create a problem for a lot of these methods. But we're going to assume certainly the way we will construct bandits in this chapter will not have a problem like that. So like the mean will be well defined. Now, if we actually know everything about the bandit, really the only thing we need to know about it to solve the problem is we need to know what these values are. And these Q values, it's all written here in the chapter as well. This just means, what is the expected reward for taking this action? Like the actual expected value. Now, there is some true value to this if, this distribution is defined for the bandit. And if we know the true value, the goal of this problem is, let's say, we're given a bandit and we are allowed to interact with it, let's say, for, some time period here. So here they use the example of we have 1,000 action selections or 1,000 time steps to work with. And then the goal would be to get the most reward possible over this time period. Now, if we know what these values are, then the problem is trivial because we would already know which action is expected to give the highest reward. And then we would just select the action that maximizes that. And we would select the same action every time, right? Because that would maximize this expected value, right? Then the long-term expected value would just be whatever this Q value is times the number of time steps that we would interact with. However, we're going to assume that we are not told anything about, I mean, we're told something about the bandit, like some range of possibilities for how the distributions are constructed, but we do not know what these expected values are for the actions. So we have to learn about, about the bandit by interacting with it. And the challenge is if we keep sampling and getting data from different actions, we can build better and better estimates for what the values are for the different, arms of the bandit. But at some point, we're trying to collect the most reward possible. So at any given moment, in this process, we have estimates, and we will have some estimate or some, tied group of estimates that appear to be the best ones possible. So, if we keep selecting those, at least that's the best we could do at that moment, because we believe that those are the best. But it's possible that others are better, and we just haven't collected enough data from them. So this is the challenge in any of these problems, and in later reinforcement learning problems, that there's this trade-off between exploitation of we're trying to get the most reward based on what we currently know, and exploration of, if we have a lot more time left in the problem, it may be worth taking that time to build a better estimate and to maybe figure out that there's some other action that is actually better than the one we currently believe is the best action. And all these methods, and the whole purpose of this chapter is going to be to have different ways of balancing the exploration and exploitation in the problem. So, are any questions about that setup? It's worth noting for very simple, clearly defined bandit problems, there are methods you can calculate for like an exact answer to this question of how to balance exploration and exploitation. But those are very special solutions that depend on a lot of assumptions, and generally they're very complicated to calculate. So what will follow in this chapter are different methods of balancing this, but the methods for balancing it, there's no like proof necessarily that these are the best methods or they converge the fastest, but they are just some method of balancing this. And it's sort of emphasized in the book that the only thing we care about is to balance it, in some way that seems reasonable, but not actually to get an exact answer. And most of the evaluation we're going to be using in the chapter is just empirical evaluation, where we'll just test things in different ways. And then from the test, we'll be able to see in practice which method ends up working well. But what is going to follow is the introduction of what are called action value methods, which will also come up heavily in the study of reinforcement learning. Here, the action value methods we're going to have a method of trying to estimate the value of the different actions. And here in this problem, that is the entirety of the problem we're trying to do. We're trying to construct estimates of these Q values, where here the lowercase q represents the actual values for the different actions, and the uppercase q represents our current estimate. And the first method we're going to use to estimate the action values is really simple. It is just going to be to take the average over all the samples that we've collected. So basically, every time we take an action, this fraction here is just the average reward received when taking a particular action. So if we have k arms in the bandit, then we're going to have basically k different averages that we need to calculate throughout the problem. Just intuitively, there's nothing more to it. This is just a more formal mathematical way of writing it, where here we're going over all the time steps, but on different time steps, we've taken different actions. So this little one indicator function is just something that only computes the sum in the case where the action matches the one that we're interested in, right? So if you imagine we have a list of all these rewards and the number of and the count of the number of times we've taken the action. And out of that whole long list, we're just going to separate out the data for each of the K actions and just keep track of the average of that. So far, right, it's quite simple. So then if we do this over time, if we were just to pick actions randomly, after a long period of time, we would have, pretty good estimates for what the expected value is. Of course, doing that wouldn't do anything towards the goal of collecting the most reward. I mean, at the end of that process, we would have a good idea of which action to select. And then if you were allowed to, take that action into the future. But here we're assuming we have some finite time period to interact with the problem. So, here, obviously, you could always just, as you're collecting data, you will have some estimate, one of these actions for which the estimate is the highest, right? And that's here. So this capital A sub t, this refers to the action which at time t is the one that we estimate to be the best action. So then the method of greedy action selection would just always select that action. And then, there's this caveat that ties are broken arbitrarily. So you could always have multiple actions that have the exact same value estimate. And then you would just want to choose randomly between those two. So when we do greedy action selection, right, we're always exploiting what we believe will give the highest immediate reward. And we don't waste any time, sampling actions that we believe to be worse. Like, the problem with this method is that our choice could be wrong at that step. And especially if we're early in the process and we have very few samples that we've taken, then there could be a very high chance that our action selection is wrong. So then, we have many time steps in the future for which, if we keep selecting the wrong action, we're going to lose out on a lot of potential reward. So it should be obvious that it may be beneficial at different points in the process to consider the other actions just to evaluate whether they're actually better. And that's where this epsilon greedy method comes in, which will come up a lot throughout the rest of the book. But the epsilon greedy method is just a method where most of the time we do select the greedy action and we just follow that. And there is some probability given by epsilon. Epsilon could be anything from 0 to 1. In practice, usually it's a small number like 1% or 10%. But with that percent of the time, we instead make a random action choice instead of the greedy action. Of course, the random action choice could also include, it will include all the actions, so it will also include the greedy action, but it also has an equal chance of sampling any of the other actions. And there's also the option of maybe changing the value of epsilon over time, like maybe lowering it to 0 as we get far enough into the future. But for now, we'll just consider the case where the value of epsilon is some fixed value. And they say, of course, that the probability of selecting the optimal action is greater than 1 minus. Oh wait, sorry. This, of course. So the point is here, if as long as epsilon is some non-zero value, if we do run this process for in the limit of infinite time steps, we will have collected enough samples of every action that we will eventually guarantee that we know the correct action. As long as we have like the expected value exists, the variance of the distributions is finite, things like that. And whereas if we do the greedy action selection, it's possible that we would actually never figure out what the optimal action is. So that is a problem. Now, right, the value of epsilon, the actual specific value will affect how efficient this process is, how quickly we get to a good answer. But it does guarantee that at least in the long-term limit, we will get the answer that we're interested in. Whereas, the other method doesn't guarantee that. So are there any questions about how the epsilon greedy action selection works?
Currently, I don't have a question, regarding the epsilon greedy actions.
Okay, but is there any other question that you do have?
Yeah, not right now.
Just a
Okay.
quick question on the
Uh-huh.
probability distribution of the actions, like that expectation value of an action that we are finding over here. Is it like pretty much similar to trying to sample data from some source and then trying to estimate its mean and its sigma? And that's essentially all we are doing in the K-Bandit problem?
Yes, although we are not estimating the sigma at all.
Right.
Notice this Q estimate is only estimating the mean because
Right.
yeah, actually knowing the sigma is not relevant for us, although it will affect the efficiency of the process. Like the higher sigma, let's say, sigma was 0. Then after one sample, we know everything about that action. And then we will very quickly figure everything out about the problem.
Yeah.
Right. But if sigma is very high, then it will take a lot more samples to get a good estimate for the mean.
Right.
So that's
there,
where it comes up.
Yeah. Is there a parallel between standard limit theorem? Like the more n I sample, I'm supposed to like sort of decay as 1 over square root of n, something like that, in terms of how confident I am in my action?
Yeah. So there will be methods that will consider. Yeah, there's like these sort of, it'll come up later, but this upper confidence bound method where the more samples we have of a given action, the more confident we are of that mean, and then that will affect sort of how often we choose that versus the others. Yeah. All right. This epsilon greedy method is just the simplest initial method, but yeah,
Cool.
there will be
And just to follow up. And there is no assumption on for different arms, the probability distribution can be like very different, right? There is no assumption on that.
Yeah, in general, there's no assumption on that. The actual test bed that comes up, this 10-arm test bed, there will actually be all of the arms will follow the same distribution with different mean values.
Okay.
But yeah, for the general problem, they could follow completely different distributions. And
Thanks.
yeah, it wouldn't matter. But yeah, we can look at the first exercise here. I don't know if anyone actually did it and wants to provide an answer. It's a very simple exercise. It just sort of checks the concept of how the action value method works and how the epsilon greedy action selection works. But here, I'll just read it out and we can sort of work through it. So this exercise is an epsilon greedy action selection. So for the case of 2 actions and epsilon is 0.5, what is the probability that the greedy action is selected? And I can sort of can write this out a little bit. So we have right, 2 actions, just 1 and 2, and then we have our Q values we have, which we don't know what they are, but in general we're gonna have v1 and v2. And now depending on, like, let's say, right, if v1 is greater than v2, then a1 would be the greedy action, right, at that particular time step. Oh, at any given point in the process, we'll have 2 different values that they could be equal to each other as well. And then, right, we have this value of epsilon is 0.5, right? So this means that we select random actions half the time. And then, the other half of the time we do greedy actions. So the question is then, what is the probability the greedy action is selected? So we can just go through here. Does anyone want to?
Well, how I thought about it was that there's 2 possibilities, which there's only one answer, but first one is that, if epsilon is, greedy or not at, a particular moment, which would, affect the distribution. So it would be, 0.5 times, 1, because if it's, the greedy action, then it would do the greedy action, 100% of the time, and then plus 0.5 times 0.5 because if it's not taking a greedy action and it's just at random, then there's 0.5 probability that it would be the actual greedy action because there's two actions.
Mm-hmm.
And so then it would be 0.5 times 1 plus 0.5 times 0.5, which I would think that it would be 0.75%, 0.75 probability that I would be taking the greedy action.
Mm. Yeah. Okay. Yeah, that is pretty much how you do it. Does anyone have any question about this exercise or how to calculate the probabilities? But yeah, I mean, normally epsilon wouldn't be this large, typically 0.5, but yeah, this is pretty straightforward. So in whatever algorithm we use, this will be, what is controlling. Like first we'll, decide whether we're in the greedy case or the random case. And then within each case, the actual selection is pretty trivial. All right, we either just choose randomly. Now, of course, the greedy selection, right, this can be more complicated if V1 is equal to V2, right? In this case, then we would actually still choose randomly between the two actions, right? Because we don't want to bias our algorithm by like always picking, V1, because that could, I mean, it probably wouldn't be, no, it actually, wait, yeah, it could be a problem if, depending on the distribution of V2, right, we could run into a situation where we keep sampling V1 and it keeps equaling this, right? And let's say action 2 actually has a small chance of giving a better reward. And then we would just always forever consider these to be tied in value because we never actually sampled action 2 again to check that it had a higher value. So you do want to make sure that you break ties randomly in these problems, so you don't run into situations like that.
I have a question, because I know you've done the exercises. I found that there is actually it claims that the experiments ran like 1,000 iterations, but with an greedy algorithm of 10%, let's say, if you have 1,000 iterations, only about 100 of them are sampling something new, and there are 10 different actions, which means that you only really get about 10 samples for each action, which is not nearly enough to estimate the Gaussian. So I was wondering how they were actually getting the algorithm to converge with such a low sampling rate.
Okay, let's get to that when we actually go through the test bed. But yeah, that'll be the next section.
Okay.
Will be all about this 10-arm test bed, right? Where we actually test this epsilon greedy algorithm. So yeah, we'll go through the details of that and see if anything doesn't make sense to people. But yeah, so here's the claim. So we talked about the general bandit problem. Now we're going to talk about a specific case where we have 10 actions. And when we construct a bandit, we take a Gaussian distribution. Now there's actually two Gaussians here to keep track of. So first of all, there is a standard normal, which we are going to use to select each of these 10 mean values, right? So basically the expected reward value from an arm will actually be 0. And then, because we're sampling 10, right, there will be randomly ones that are greater than 0 and others that are less than 0. And here we see an example of one of those samples. Now, then each individual action will then, its reward distribution will be given by a Gaussian with variance 1, and then the mean that was, randomly sampled in the setup part. So here's an example of one of like a randomly created bandit, right? Where you can see that with this sort of this violin graph that each arm actually has, right, the same variance, but their means are shifted around. So here's an example of one. Yeah, and here's, of course, if I keep clicking this button, you can see this is what it looks like when you just make, every time I click this, it's just going to make a new bandit. And you can see the rewards are always following the same, the same distribution to select the means. And then, each one is always going to have this unit variance. Does that make any questions about how these bandits are actually constructed? I can also change this to like, make like 50, and you can see there will be way more things, so we could make a 50-arm bandit and it would look like this, or we could make, a much smaller one. But for this problem, we're just going to stick with size 10. Well, we can also look at some of the results we get when we change the number of arms. So to do these tests, right, where we're evaluating methods, they're going to generate 2,000 of these bandits. And then for each bandit, we're going to do a run of these methods. Actually, how long? Let's see. Okay, for 1,000. So here in this example, they're doing a run of 1,000 steps, but they're doing the method over 1,000 steps over 2,000 different trials, right? Where each trial is also done on a different one of these bandits. So that's how we're sort of randomly sampling the success over this type of problem, right? Because we're sufficiently randomizing all of the trials, or we're not going to wind up with a situation where a particular bandit, was easier to solve than others because we have 2,000 of them that we're using as samples for all of the problems. Okay, so then the method we're going to use is the one described with the epsilon greedy action selection method. So we go through the time steps, and along the way, we keep track of these averages, right, for each arm. And then depending on the value of epsilon, we either select the action, the greedy action, or we select a random one. And either way, we always collect the data along the way, regardless of whichever action we pick. And over time, we improve the estimate. And then what this is measuring, what this graph is measuring, is the average reward, over time, the cumulative average, right? So this is like by the end of the process, what was the average received? I think, wait, from start to finish, or is it averaged over? Oh, you know what? No, I think actually, because we have the 2,000 different trials that we're running, I think, no, this is the average reward on that particular time step, right? But it's being averaged over the 2,000 different runs that were being done of the experiment. So here, I have this, here is code for doing this, but I mean, this is just, this generates the sample of a bandit. So like the bandit itself is defined by this Q vector, right? Where the vector just defines what the mean values are for each arm. And then the A here, and then in order to do a sample, you just generate a Gaussian and then add the average to it, right? Because the variance is unchanging. And then this simple algorithm, what it does, it goes through, it gets the actions, it finds the argmax of our Q estimates, which we're keeping track of. We have to keep track of actually the Q estimates and the count, right? So the visit count. So we can collect the average at any given time. We're always, this will come up later in the chapter, but there's a way to actually calculate the sample average in an incremental fashion so that we don't have to keep redoing this sum, this sum over and over again. We can actually update it from an existing value. But even though it looks like there's a lot of, I'm also keeping track of other variables here so I can make plots with this. And there's other methods built in here. But we use this to evaluate the epsilon greedy algorithm. And then here I'm just averaging all of these runs together. So here, this plot will look very similar to the plot in the book. I've also added here the theoretical limit. So what this line represents is, obviously I know, because I generated the bandits, I know for each of them which action is the best. So this line is saying if you actually just cheated and picked the best action from the start, this is the value, the reward value that you would get. It's still, the reason why it's still noisy is because, I'm actually still collecting the samples from the bandits. Right? I'm not just taking the mean value. So there's two plots here. The first one is showing the actual, reward value we get over time for different values of epsilon. And this is showing the percent of the time that we actually chose the correct action by, whichever one is the best. So, right, the best you could do here is 1. That would mean you always selected the correct action. And then, right, this value of epsilon of 0.1 is at least over this number of time steps has learned the fastest, how to get the correct action a higher percentage of the time than any of the others. We can see here the greedy one, it, about 35% of the time, it was able to, get the correct answer for the greedy action, but that's not a very high success rate. And we can see that it's also not improving at all, because we wouldn't expect it to improve. Like, this is very quickly going to, depending on how we initialized all the Q estimates, right? As soon as this one finds an action with an estimate higher than all the others, it's always going to select that. And because, the variance here isn't that high, like, it's possible if it thought this action was the best, that, let's say it got a sample. So like here, like if you look at this plot here, we can see that action 3 is the best, right, for this bandit. But, action 5 is kind of close to it. And it's possible that we collected some samples of reward from action 5, which are up here, and that action 3, maybe we collected a sample at the mean. So then this would appear to be the best. Now, if we only do greedy action selection, we would keep selecting action 5, but over time, the average would move to here, and it would eventually, fall below our estimate here, and then we would actually get the correct action. But, the problem is if we initialize all our values at 0, let's say, any action we select that has a mean which is greater than 0, like let's say, action 4, if we keep selecting it and our average never drops below 0, then we would just select action 4 every time. And obviously this is not the correct action. So we're sort of we would have to rely on the fact that we get lucky enough to collect enough samples from the best action that, it would actually be the highest estimate. But we can see that only happens about, 35% of the time here. Now, okay, your question, so someone's question was, how is this method working at all if we only do it for 1,000 time steps and there's 10 arms? So if we selected randomly every time, right, then we would only have 100 samples from every action, and that's not very many. So again, like, we don't need to have a perfect sample estimate for every action. And what's going to happen actually is, let's say, we have these actions down here. Even for the epsilon greedy method, it doesn't take that many samples from here to realize that the average is below 0. So what's going to happen is the algorithm is just going to very rarely even bother checking these actions. Like, of course, there's a 1 out of 10 chance of checking them when we have the random action selection. But in the greedy part of the algorithm, where we are going to end up having to choose between a few of these top actions, most of the greedy action selection samples, right? Most of them are going to be between maybe just 2 or 3 actions, right? So that it does end up being enough samples to, we only need enough samples to distinguish the actions from each other, right? We don't actually need enough to get an exact answer for anything. And of course, these methods are not doing perfectly well. Like at the end of, with epsilon equals 10%, right? We only reached 80% success rate, like on step 1,000. But, I can change these values and we can see, like, if I make, right, this epsilon 0.5, like we had in that other example in the book, we can see what happens. So, yeah, this is now even worse. So actually, is that right? Yeah, this is worse than the greedy only method. Even though, so if half of the runs are taking an optimal action. Yeah, it seems like if half the runs are taking an optimal action, it would be better than this method. But I guess what this means is that out of the runs that have not found the correct action, they may have still found like the second or third best action. Whereas here, the rest of the time we're actually taking random actions. Also, this actually has to be 0.5. Or no, that actually does seem pretty high. So, if you set epsilon high at 0.5, at the end of 1,000 time steps, we probably have better estimates than we have for any of these methods. But of course, the only way we've received those better estimates is by sampling so much in this part of the process, right? So then if we were to continue this, and now if I were to go to here and then set epsilon to 0 for the next set of time steps, right, then this might be the most successful. But that's a different experiment to set up, right? So if you wanted to have your best shot of knowing the best action at the end of 1,000 time steps, right, then you would actually want to set, epsilon to 1, right? Because you want to, well, even that, I'm not sure, because you actually will need to distinguish, the challenge is eventually to be correct. You have to distinguish between like the top 2 actions, right? So in the future, you should devote more of your samples to the ones up here. So, but it's going to depend on some complicated function of, what our variance is in the estimate for these samples out here. And there could be other samples here where we have so few samples that we still need to end up collecting them, right? Luckily for this problem, we are told that these all have, the same variance. So we don't have to actually worry about, our variance estimate also being wrong.
Yeah, this brings me actually to another question that I have. Or I think it's not exactly a question. These algorithms, if epsilon is greater than 0, it never converges, because even if it finds the optimal solution, it will still try to sample other actions.
Oh yeah.
So
yeah. So what converges is this.
Mm-hmm.
This will converge to the correct values if epsilon is greater than 0.
Yeah, but the action choice will not converge.
Yeah, the action choice will not converge. Now we can lower epsilon to 0 on a time a schedule.
Yeah, that's what I was thinking.
Yeah, but of course, that's where the balance comes in, because of course we don't know that we're correct until these values have converged. These values won't actually converge until we have infinite samples. But there's a point where they've converged enough where we have a high enough confidence, right, that we'll end up, selecting the greedy action most of the time. But, the epsilon greedy method works pretty well on this problem, because even if epsilon is kind of small, like 0.01, when we get to this end part of the process, it will automatically do the thing I mentioned, which is just spending most of the samples between two very close actions that appear to be tied. Because like you want to eventually break the tie, and right, like if we collect more samples of this, and we're always going to collect more samples, and they're going to be skewed towards the actions that have the higher value estimates. So it's going to naturally do what you would intuitively want to do, which is collect more data from the part of the problem that you think has the correct answer, even if you're not. Like, we're sort of narrowing down, right? Like, I mean, eventually, of course, the epsilon greedy method is not perfect, because like at some point we're going to know with very high certainty that this action is not worth sampling. The epsilon greedy method will continue to sample this action though, right? Because it's random. There are other methods we'll look at that will do something different. And right, there will be certain actions that are almost like completely ignored later on in the process. Yeah, but that is the, at least these initial graphs of the test bed. And there's some discussion here which might clarify certain things. Oh yeah, so we're saying if the reward variance is larger, then yeah, that poses even more of a problem for the greedy method, right? Because like if the rewards are, if the variance is larger, we have I think just a higher chance of not getting lucky with having selected the actual greedy action. But again, that also depends on how we've initialized the value estimates, which we'll see. In this, I think the way this is done here, the initial value of Q, yeah, is 0 by default. And there'll be a method that will actually change that as another method of exploration. Okay, so are there any more questions about at least this evaluation plot? Yeah, we can move on then to, I guess, these next exercises. Again, just sort of checking knowledge of how this algorithm works. So we'll see. I think it is worth going through can look at the first one of, let's see, 2.2. So, okay, let's see. We have, okay, consider a KR bandit with 4 actions for 2.2, 1, 2, 3, and 4. Consider applying a bandit algorithm using epsilon greedy action selection and the sample averaging method. And then there's a list of results that happen on different steps. Okay, so here, I'll write down, so we have, the action selected. And of course, this is all going to be like per time step. So the initial action is 1, right? So we have the action and the reward received on each time, right? So we select action 1 and get a reward of -1. And then we take action 2 and get a reward of 1, right? And then we take action 2 again and get a reward of -2. And then we take action 2 again and get a reward of 2. And then action 3 and get a reward of 0. And then the question is, for each time step, what was the algorithm doing on that time step? So, one way to solve this problem is, right, for each time step, we would like to know what the value estimates are or have been. So, and also, right, action 4 is never selected, right? So, right, we start out with our, you can write this down where you have all of the Q values, right? So we have Q1, Q2, Q3, and Q4. So they all start out at 0. So here, I'll write, like the line I write this on will be, this will be what the values were prior to the action being selected. So then, right, we had action 1 selected with a reward of -1. So we only have 1 sample. So then if we update this, we have our Q value for action 1, right, is -1. And then the rest are still 0. Right, now on step 2, now we have a new action, action 2, and we receive a reward of 1. Right, so now we still have our sample of -1 here. This is 1, and these are both 0. Now we get a new sample from action 2, which is -2. Right, so now our expected value for Q1 is still -1. Right, but now for Q2, we have 2 different samples. Right, we have a sample of 1 and -2. So our sample average for that should be -1/2. Right? Does that make sense to everyone? Because we have 1 minus 2 divided by 2. And then we're going to add to that. So then, now we get a new sample with a reward of 2. So then now we have 3 samples, right, where the sum is now 1. So it's just 1. So now this is going to improve to 1/3, 0, 0. So as we go through the algorithm, like these are how the actual values will be updated. But we haven't been told what the value of epsilon is or what happened. So in order to answer the question, which is on what steps was it the epsilon case, or on which steps was it, definitely the epsilon case or definitely not the epsilon case? Oh, sorry, this screen share broke for some reason. But does anyone have a idea or want to propose a way to, answer this if we, like, after we've constructed this list of what the value estimates are on every step? Because I can just show this solution where I've sort of created this table in the notes. It should match what I had written in the notebook, right? This is where I wrote down, right, what the Q value estimates are on every step, right? So our final estimates from collecting these samples, right, are -1, 1/3, 0, 0. So the next column here, I've specified, what actions are in the set of greedy actions. So when we start out, all of the actions appear equally good because they all share the same estimate of 0. And then after the first action, right, since we got a reward of -1, now actually the other 3 actions that haven't been sampled from yet all appear to have the best reward. So the greedy action set would be 2, 3, and 4. So on each, row, we can look and we can see, which actions. It's only actually, right, when we get to this row, action 2 appears to be the best, like uniquely the best. And then at the very end, it appears to be uniquely the best. So, right, we know that on step 1, we selected action 1. And that happens to be in the set of greedy actions. So, right, here this column says, was a greedy action selected? And if a greedy action was selected, then we don't know what the algorithm did. Like it could have either selected a random action or it could have selected the greedy action. It's only when we actually select an action which is outside of the greedy set, which happens here, right? At the very end, we have a belief here on this step that either actions 3 or 4 are greedy, and yet we select action 2. And then at the very end, we believe action 2 is the best on this step, but we actually select action 3. So that means that in order for that to happen, we had to be in the epsilon case of the epsilon greedy algorithm. So any questions about this exercise, how the estimates work? Because yeah, we can just try to look at the next exercise, which is relating to this figure, right? This one. But the question is, which method will perform the best in the long run in terms of cumulative reward and probability of selecting the best action? How much better will it be? Express your answer quantitatively. But we can first think about it qualitatively, which is, comparing these methods. And for now, we're only comparing, right, these 3 methods, right? So we have the epsilon greedy method, the epsilon value of 0.01, and the epsilon value of 0.1. And we've only done this for 1,000 time steps. But the question here is, in the long run, which will perform the best? So yeah, does anyone have an opinion on that or want to?
I mean, the largest epsilon will probably give us much better estimate of Q values, and then we can use those to get the maximum reward in the long term.
Okay, but remember, we're not allowed to change the value of epsilon. So this is asking if we continue with this algorithm, like this style, right, where we just extend this plot right out to the right. Which would we expect to do better over a longer time horizon of doing the same thing? And there's, these 2 criteria, right? One is the probability of selecting the best action, which is down here. And the other is the actual accumulation of the best reward. Any idea?
Well, at least for the epsilon, well, one thing that I thought was that for any epsilon, it wouldn't converge to the theoretical limit, which would be the ideal because of the probability, because that probability of taking a random action will always be there, and since we're not decaying it, so it cannot converge to the theoretical limit, I think.
Yeah, that's true. But we're asking which of these will do the best in the long run, not which will actually. Yeah, none of them will achieve the theoretical limit. And actually, you can say more concretely, like let's say we have epsilon of 0.1. What is the best that this could do in terms of selecting the optimal action?
Well, at best it could reach the theoretical limit, but then
well, no, I mean it can't,
that
because
theoretical limit 90% of the time, but that epsilon of random action would interfere that 10% of the time. So
yeah. So the best it could do in theory is selecting the optimal action 90% of the time. It's actually better than that, right? Because even if we take the random action, we will still select it 10% of the time.
Yeah.
So it's more like, it's a little higher than 90%. But, like that's the best it could do. So, I mean, and part of that actually, does sort of hint at what the answer is for the, which will do
But
best
then,
in the long-term limit.
At least, given, the graph, currently, if under the assumption that, the performance improvement for the epsilon being at 1%, it would increase, continue increasing, then eventually it would do better under the assumption that, it doesn't plateau. But, a lot of times in a ML algorithm, usually, having a different epsilon, causes a different plateau usually. So
That's true. However, in this case, this problem has some nice theoretical guarantees. And one of them is that for any epsilon greater than 0, it actually is guaranteed to reach its theoretical limit, which is nice, at least for this problem.
well,
For
then,
these bandit problems. So actually here, let's like just cheat and actually extend the graph so I can make it, I'll have it go for 10,000 steps. Hopefully it doesn't take too long. Okay, so before we had the plot just to here, right? And we clearly had, right, 0.1 winning. So now, right, we can see what has happened over time. Right, we can zoom in a little bit. So yeah, before we had seen the plot out to here, and now we've extended it further. Let's see how we can look at this plot too. So this is the percent of time. Now, interestingly, in this plot, this is actually still seems to be underperforming this one, but you should be able to see how while the green line has completely plateaued, this one is still on a upward trajectory.
well, I
And
guess,
if I were to
if
do
the
this,
theoretical optimal is guaranteed, then, having a very low epsilon would be the best one in order to, lead to the best convergence, though the problem with that be that it would converge really slowly.
yeah, so let's look at this one now. I've made it even smaller, 0.001. We can see, yes, it is over this number of time steps. It is still failing 40% of the time, but it's not even close to plateauing yet. But yeah, this will take a much longer amount of time steps to succeed. Also, remember, this is just showing the percent of time the best action is being selected. It doesn't say how far away it is from the best action. So, right, it would look as though this method should really severely underperform this one. But actually, with the average it's collecting, it's not as bad, because probably even though this is only selecting the optimal action 60% of the time, the remaining 40% is might be like, the second or third best. So it's not as bad as it looks in this plot if we look here. But here we can see, we can answer this, a little more precisely. So here, I'll just show this. So in the long run, right, both of the epsilon not equal to 0 methods will converge to the true mean value. And right, they're each going to select a random action 10 or 1% of the time. So we can calculate for any value of epsilon, once it's converged, the percent of the time it will take the correct, the greedy, or the optimal action, which is 91% or 99.1%. So basically, the smaller the epsilon, the better for the long run performance. For the epsilon equals 0, so the greedy case, the expected reward and optimal action, right? It depends, I already mentioned, it depends on the order of when the actions were sampled, how likely it is to have gotten the best action. It's not that straightforward how to calculate this, right? We can see from these plots, this limit here, it appears like, okay, 36.7%. I don't know if I were to run this again, if this value would change. 37%. I think when I was doing it before, it might have been more like 38% of the time, but it's somewhere around this, 36 to 38% of the time with this method set up. we end up getting the correct action. And then the actual sampled reward, it doesn't just depend on this probability, right? It depends on like the probability of getting the second best action and the third best action, etc. And that ends up being, a value of around 1. But, this reaches a plateau very quickly. We can see like there's no improvement happening here over a long period of time. And the problem with this method, the reason why it's not improving in this method, even though this is slow, like this is still going to continue to improve to its own theoretical limit, is that, we don't have a guarantee of having sampled enough data to actually get convergent Q value estimates. So the other part of the question was the long-term reward based on, so in order to calculate the long-term reward, first of all, you need an estimate of what is the expected reward for the best action in one of these problems. And it turns out, if we look at the theoretical value here, it's about, 1.58. We'll see. If you're interested, I have some more details about why, how to get this value or a different way of calculating it. But somewhere around, close to 1.6. And then once these have converged, we would expect them to get that reward. Wait, this percent of the time. Actually, wait, this calculation is, oh yeah, no, sorry. Yes, this is correct, because the other time, right? Like the time when we're not selecting the optimal action, we're selecting a random action. And for these problems, the expected reward from a random action is 0 because of how the bandits were set up, right? We're sampling the rewards from a Gaussian. So we would expect for any of these Gaussians, right, for any step in which we select a random action, our expected reward is 0. So we don't have to include it in this expected value calculation. So this is the expected long-term step reward for the 0.01 epsilon method is about this, where I'm using the value of 1.539 for the value of the best action. Yeah. I mean, in the long run, once these have converged, the early behavior doesn't matter anymore, but, you could also, accumulate this over time. That would be taking the integral of these plots. And that would give you a different answer depending on if you care about, what is getting the best result at the end of this process or what is got the best result accumulated throughout the process. It depends on the shape of these curves. Yeah. So any questions about this exercise?
Is there a general formulation for how the slope or the curvature of the curve should depend on epsilon?
No. So not as far as I know. I mean, the rate of convergence of this depends on sort of the ordering of sampling and when you expect a given sample estimate to, leapfrog another and how good it is. We can answer a few more questions about how this bandit problem works. It depends on the distribution of these order statistics. Like we need to know like the probability that a sample from what we believe is the fourth best action is actually, better than the best action or the, so there are these complicated order statistics you have to calculate. Mm-hmm. And I'd say it's not very straightforward, but you can get some idea of how complicated it is in this next part, which I have, which we can go over a little bit. So they don't talk about this in the book, but if you're curious, you can actually calculate like what to expect from one of these bandit problems. So like we know, right, that we are generating the arms from a standard normal. Now, we're interested in the reward of the best action. Now, for a random problem, like we know for any given problem, like they showed an example here, right? And this one, like the third arm has the max reward and it's like 1.5 5 or like 1.6 or something. So the question is, can we say something about for a random bandit selected in this method, what do we expect the best reward to be? And that is this. So this is, what is the expected value of the maximum of k random variables where each random variable is selected from a standard normal? Okay, this is just like, this is the distribution of the best reward for a random bandit, right? So you can write this down more simply. Like there's different ways of characterizing a probability distribution. For this problem, the easiest thing to start with is to think about the cumulative distribution function here, right? And this is the probability that a random variable is less than a given value. Okay. Now for this problem, a random variable is actually the maximum of k other random variables. So we can write down this distribution function as the product of the k other distribution functions, right? Because in order for this to be the maximum, like in order for this to be true, it means that all of the other random variables have to be less than x, right? And that's what this product is. This is checking that all of them, right? Because we're taking the maximum, so they all have to be less than x. Okay, so now let's say this, we know a lot about standard normals, Gaussians, right? We can look up what their distribution functions are. So I'm not going to write down the whole function right now. I'm just going to say the distribution function is just this capital F sub g, and the density function is just lowercase f sub g, right? So, and the density function is just, did I write it down here? This is the density function, right, of a standard normal. It's just this, e to the negative x squared function. Okay, so now the distribution function we want for this thing, the R max, right, is actually, all these have the same distribution. They're all Gaussians. So we just have to take the Gaussian one to the kth power. Now we want to get the density function from this, right? The density function is akin to
Hello. Hello, Kamaru.
Yes?
Yeah.
Oh, sorry, Kevin, did you have a question?
Good morning.
Oh, I don't know. If you have a question, you can unmute and ask it. But so we want the density function, and the density function is just the derivative of the distribution function, which we can calculate here just with the chain rule pretty easily. So we just have the value k, right, and then we have the old distribution function to the k minus 1 power, and then the derivative of the density function. Now the derivative of this is just the Gaussian density function. So we get this pretty, simple looking form for the density function that we care about, right? Now, it's actually not that simple because, right, like the distribution function, like here I've expanded this out. So the density function of the Gaussian, pretty straightforward. It's just this exponential function. The distribution function is the integral of the density function, which there's a shorthand for it, capital phi, but it's also this, these are other ways of writing it, but we're still writing this, right? It's still this integral that we have to deal with. Luckily on computers, numerically, this is not that challenging to deal with, but it is difficult to actually write down something, like an analytic answer to this. But we can, at least with most of our computer tools and programming languages, we have access to numerical approximations to these functions. If we want the expected value of R max, we have to calculate the integral of this expression, which is not easy to do. We can do it numerically, which I'll show later. But there's other expressions people have come up with. You can actually write down analytic expressions or an upper bound for this expression. So this is one of the upper bound expressions. It's just the square root of 2 times the natural log of k. This upper bound is pretty far away from the true value that we actually see. There's also an asymptotic limit to this, which is this expression. And this will converge to the true answer in the limit of k going to infinity. But you can see here, this is the order of the error term for this approximation. And you can see this is 1 over the natural log of k. This error term shrinks very slowly, right? I mean, like the log of, 10 billion is like it's a pretty small number. So this also is not a great approximation, but it will end up being, closer than the upper bound. For k equals 10, this is 1.6, right? The value we actually were seeing here was like 1.557 or something. So it's not terrible. Easier to do since we have access to the tools. We can actually just compute this integral numerically because we have access to these functions. And that is what I'm showing here. Actually, a little cramped, so maybe I can make it a little wider. But what this plot is showing is this blue line is the density function for the best arm of a random bandit. And this is, if we calculate the expected value numerically, we get 1.539, which, sort of matches what we're seeing here for the 2000 trials that we've taken. The dotted line here, this is the expected value, right? It's skewed from the peak. The peak is the mode of the distribution. This is a skewed distribution. It's skewed to the right. So the expected value is greater than the mode. And then this solid black line is the asymptotic limit. And the red line is the upper bound. So it's kind of far away. But if I make this like 100 arms instead of 10, we can see how the distribution shifts and it gets, I think, a little closer, perhaps, on a percentage basis. I think the actual distance here won't converge very quickly, but, right, if you look at this order term, right, it's sort of it's multiplied here. So the percent error of this is going to 0 very slowly over time. This is actually showing the expected value of all of the arms, right? So this blue curve is showing the distribution of this far right bar here, right? Where this is the expected value is 2.51. About these values are actually sampled though. This is more precisely calculated with the numerical approximation. This is showing the expected value for all of the arms. So this is like if we generate 100 arm bandit with this method, this is what we would expect from the reward of each of the arms ranked, from 1 to 100. Right, so the worst one we'd expect to be negative 2.5 about, and the best one 2.5, and of course the average arm we'd expect to have a reward of 0. And this is showing how, as you add more and more arms to the bandits, just because of how we're constructing them, the reward of the best action will, grow. I think unbounded, right? That this won't actually have any limit. We're seeing this is a log scale on the x-axis, and this is continuing to increase. So, right, if you look at this formula for the upper bound, right, it does grow very slowly. Right, it grows as the square root of log of k, so it grows very slowly, but it is growing to infinity over time. Yeah, with the upper bound staying up here. So, this is like more, we can say this about, the arms and how the bandit actually looks, but this is just sort of extra detailed stuff. It's not actually necessary to solve these problems, but it gives you an idea of why, like, we get this value of about 1.54 when we make bandits in this way. So, right, this is just the expected value though, right? This whole density curve shows you, right, out of the 2,000 bandits we generated, a lot of them are going to be in this zone, and then, you know, there'll be some where the best reward is very high and others where it's as low as it could even be, you know, as low as 0. Yeah, but any questions about this sort of theoretical detour? It's not too important for the rest of the chapter, but it might be, you know, interesting if you want to know what these bandits end up looking like. Okay, well then, to finish, I guess, our discussion for today, we can just talk about this section on incremental implementation, which is about how do you efficiently calculate the sample average. So we know that for a given action, let's say we just have samples from a particular action. This is how we calculate the sample average, right? We need to sum the rewards and divide by the number of samples. And we could redo this every step. Like, we could maintain a vector, like a list of all the rewards, and then we could evaluate the sum, but that's very inefficient, both from a storage perspective, because we have to store all of these reward values, and it's also inefficient computationally, because we have to recalculate sums that we've already calculated the whole time. And it turns out, so this incremental implementation shows a way of updating the sample average, and only keeping track of the sample average. Now, there's another method we could use, which is actually simpler conceptually, but it does require keeping track of two things. And it's actually what I did in this problem, because more complicated methods will actually require keeping track of both values. But you could imagine, let's say we're willing to store two values. So if one of the values we store is the sum of rewards, then every time we get a new reward, we can add that to the sum, right? So we can accumulate the numerator of this expression. Now, the denominator will just be a value of 1 every time we get a reward from that action. So we just increment the denominator by 1 every time. Now, if you keep track of both of those, you can just update the numerator and then update the denominator. And then every time you want the Q estimate, you just divide them. And then you're just doing one division. So you have to do, you know, 2 additions and then 1 division to update. Say 2. Yeah. Actually, I don't even know if, other than the storage, the extra storage requirement, I don't know if it's actually less efficient. Yeah, what did I say? 2 additions, 1 division. This is, yeah, I think actually computationally it's the same as this method. Right, this is 2 additions and 1 division. But the difference is, you know, this, we actually only have to store one value. Well, we're keeping track of n anyway. Yeah, actually, I think it ends up being exactly the same, the same method, because, right, to even do this method, we have to keep track of n. Like, we're just assuming that we have a count of n. Yeah, because we have to keep track of a different n for every, for every action, for the sample average method. The reason for writing it down this way and deriving this is because it ends up leading us to this other method of using a constant step size, where it turns out if we write down the update rule like this, so what this looks like is we have this quantity. Oh, I actually have to fix this. This should be minus here. Sorry. So, right, we have this quantity in the brackets, which looks like it's some sort of error value. right? It's the difference between the reward we just sampled and our current estimate. And this update rule makes it look like we take our existing estimate and then we add an error term with some constant. And this constant you can think of as a step size. And in the sample average method, the step size is always 1 over n, where n is the number of samples we have collected so far. But we'll see that we can actually replace it with a constant value, and it will compute a different style of average, which will still converge to the sample average in the case of a stationary problem. But in a different type of problem, it will be useful for updating values where we expect the values to change over time. But again, we're going to be, empirically evaluating this method, even though, we could make theoretical statements about it. But the easiest thing for these bandit problems is just to actually test out a bunch of stuff. Like we tested out the different values of epsilon to see how quickly they converge. But this derivation, the way it proceeds, is very similar to a lot of other derivations in the book, where we sort of make use of a recursive formula, right? So here we take this sum and we separate the final term out of the sum, right? So now we have the sum from I is 1 to n minus 1 instead. And then we multiply by 1, which is just multiplying and dividing by n minus 1. Now, the whole reason for doing this is that now this right-hand term looks the same as this expression we had, right? If we just change n to n minus 1 in this expression, then it's the same formula, which means that by the definition of q, we can replace this whole thing by q if we replace n by n minus 1 in the original definition. And that's what we do here. And then after rearranging some terms, we arrive at this update rule, which is this recursive update rule, making use of expanding out the sum. But, you should take note of how this derivation works, where we sort of adjust the formula until we get something that looks like the original definition we had. And, right, the way this is like our new estimate is the old estimate plus some constant, which we'll call a step size term, times target minus old estimate, which is some kind of error value. And this type of update rule will come up in a lot of the other algorithms. And, we can do, for the next session, we'll start talking about the non-stationary problem, which for this problem, it will be more useful to change the step size in a way where we're no longer computing the sample average, but we're computing an average which is weighting more recent samples more than samples in the past. It's something called this exponentially recency weighted average, as opposed to this is computing this true sample average. But the other thing you can notice about the sample average is that if we think of this as a step size, the sample average is computed by doing this style of update, where the step size is converging to 0 over time. And it's converging to 0 at this rate of 1 minus n, where n is the number of samples. So, you can write it down this way. The other thing I said, which might be a little easier to visualize, is that when you do the update, you first of all, you increment n, or you know what n is, like, let's say. And then the only thing we really have to update is, right, we have to update the numerator here. So we add the next reward, and we have this running sum. So the thing we're actually tracking in real time is the sum of rewards. And then whenever we want the q value, we just divide it by n. Here that her division step is done inside of this update here.
Wouldn't it be better to actually have just keep recording the average and the number of and the n rather than a sum, because sum can really grow a very large number, right?
Yeah, that's what this method does.
Okay.
It doesn't keep track. The actual thing we're storing and updating is the average. Yes, the sum can grow very large, although, yeah, that could be a concern if you're worried about the number overflowing. Practically for most of these problems, it won't be too big a problem. But yes, it is true that if we do it this way, we don't have to worry about the values blowing up. So that could be an advantage. So yeah, I think, yeah, next time we'll do the non-stationary problem and go on and see how far we get in the chapter. And yeah, we'll stop there unless, or if there are any more questions, I can answer them now. And this is, yeah, the pseudocode for the simple algorithm using the incremental update rule. Although, given the concern that you said, actually, n will be growing in this process.
Yeah.
So if you're worried about that, this will always be a problem. But, you know, we're dealing with integers. Hopefully, we have enough integers to deal with. If n actually gets too big, it's likely that our computer won't even be able to handle whatever, you know, simulation we've asked it to do.